Alright, chapter 5, standard deviation as a ruler in the normal model. So sometimes in statistics we need a way of comparing two things that are not obvious and easily comparable. In order to do this, we use what we call z-scores. All z-score is a standardized value that is obtained in the following way. We take the value subtracted from the mean and then divide it by the difference, or divide that difference by the standard deviation. So formula for z-score, your point minus your mean divided by your standard deviation. You will have to find z-scores. That's not a hard formula to remember. Now, first example.
So y minus y is the mean?
Yeah, y bar is your mean here. So y is your point minus mean all divided by s, which is your standard deviation.
Mm-hmm.
Everybody okay with that? Okay. That was a horrible y bar. Alright, the first example says Jacob and his twin sister Jessica both go in for a physical. They both get weighed. Jacob weighs 210 pounds and Jessica weighs 170 pounds. The doctor tells them that the average weight for men in the U.S. is 195.7 pounds with a standard deviation of 43.1 pounds. And the average weight for women in the U.S. is 150.7 pounds with a standard deviation of 31.4. Which one weighs the most relative to their gender class? So, if we looked at this, we can obviously see Jacob weighs more than Jennifer. But on average, men weigh more than women, right? So it might not necessarily be a fair comparison. So what we're going to do instead is compare each of them to their own gender class and then see who's further off compared to their gender class. Okay. So for Jacob, I'm going to erase this. We'll do his first. For Jacob, his z-score would be his weight, which is 210 pounds, minus the average weight for men, which is 195.7 pounds, divided by the standard deviation for men, which is 43.1 pounds. Okay. Let's see if I can pull up my TI-84. I hope the air conditioner kicks on soon because it is hot. Okay. So if we do this, 210 minus 195.7, and we'll divide that by 43.1. Okay. So what we get is a z-score of 0.33 approximately. Okay. Now let's find the one for Jessica. So we've got Jessica. Okay, we're going to take her weight, which was 170, and subtract it from the average weight for the women, which is 150.7. And we're going to divide that by that standard deviation, which is 31.4. Okay. So we will do 170 minus 150.7 and divide that by 31.4. We get 0.61 approximately. Easy enough? Okay. Now from this, what we can tell is that Jessica weighs more in comparison to her weight class than Jacob does. Okay? Does that make sense? Okay. Now, that might seem pretty obvious comparing 210 to 190 versus 170 to 150, right? Because the difference here is what, about 15, the difference here is about 20. but don't let that fool you because your standard deviation kind of start another one. All right, so does it ask specifically in the question, which one weighs most or weighs the most relative to their gender class? Obviously the answer here will be Jessica. Okay, so we answered that first question. All right, z-score is measured the distance of the value from the mean and standard deviations. Okay, so a positive z-score indicates the value is above the mean. A negative z-score indicates the value is below the mean. Does that make sense? Okay, both of these here were above the mean. If they would have been smaller, if Jessica would have weighed 140 pounds, it would have been a negative z-score, which means she was below the mean. Okay, and that's all that says. A small z-score indicates the value is close to the mean. A large z-score indicates the value is far away from the mean. So the closer it is to 0, the closer it is to the mean. The further away from 0, the further away it is from the mean. Okay. So let's do another example. This one says a South Carolina farmer planted several fields of corn and peanuts back in 2017 when the world was normal. His best corn field netted him 212 bushels per acre, while his peanut field netted him 5,214 pounds per acre. He was convinced that compared to the state averages, his peanuts were his most extraordinary crop that year. State corn averaged 136 bushels per acre with a standard deviation of 28 bushels per acre. All-state peanuts averaged 4,000 pounds per acre with a standard deviation of 670 pounds per acre. Was his assumption correct? Or was he right in his assumption? Okay. So, if I'm just looking at that off the cuff, it's kind of hard to tell. 5,214 pounds is a whole lot of pounds. 212 is a pretty good bit of bushels, right? Especially compared to the state averages. Okay, so if I'm just looking at those right off the bat, I can't really tell whose was better than the other. He thinks his peanuts are because it's more than 1,000 difference. Here it's less than 100 difference. Pretty close to an 80 bushel difference, right? But how do you compare bushels to pounds of two different crops? You really can't. But what we can do is compare each to their averages. So if we use z-scores, we can find the z-score. Let's do peanuts first. The z-score for peanuts. So sometimes when I'm doing z-scores, I want to differentiate them. I don't want them to both be z. I'll just write what it is kind of in a lower subscript. Okay. You can even do an abbreviation if you want to. If you want to do z sub p for peanuts and z sub c for corn, I don't care. Right. Just keep them straight. Okay. So my z-score for peanuts, we're going to take his average of peanuts, which is 5,214. We're going to subtract that from the state average, which was 4,000 pounds an acre. And we're going to divide that by standard deviation of 670 pounds. I'm going to go ahead and write the formula out for corn too so I can do them both when I pull the calculator up. His corn was 212 bushels an acre. State average was 136. Standard deviation was 28. So let's see which one had the better z-score. Okay, 5,214 minus 4,000, and then divide that by 670. We get 1.81. We'll look at 212 minus 136, and hit enter first because if I divided it, it won't turn out right. And divide that by 28. 2.71 approximately. So he thought peanuts were most extraordinary, but according to z-scores, corn was. Right? The bigger the z-score, the more extraordinary. Further away from the mean, the better, right? In this situation. Right? So you want to be higher than the mean here because you want to produce more. Right. So in this case, it says, was the farmer right in his assumption? Say no. Corn was his most extraordinary crop. fairly certain I spelled extraordinary wrong, but this is not an English class. Alright. Everybody okay with z-scores? Now, let's look at transformations. Now, if you've done transformations in like Math 108 or some other math class, they're kind of a pain. These really aren't that bad. Okay, because we don't graph here, not in a traditional sense. We're just going to look how stuff shifts. Okay, so during the months of June and July, I sell vegetables at the local farmers market because the school doesn't pay me during the summer, which sucks. Alright, so for the 8 weekends during those months I went in 2018, I made the following amounts. So 500 the first weekend, 600, 625, 600, 700, 650, 520, 350. This year I plan on increasing my sales by $100 every weekend. First, find the following measures of the original data set using the one-var stat function on your calculator. Okay, so what we'll do is we'll type in this simple list, we'll find our mean through our range, and then we'll basically do a transformation and see how they change. So, pull this over here so I can see my numbers. I'm going to go stat edit, get my list. 500, 600, 625, 600, 700, 650, 520, 50, and I'm done. All I have to do now is hit stat calculate one var stat, make sure that L1 is the one that's typed in, and hit calculate. Okay, so what it does, I'll scroll over here. This one I really wish that the board kind of lined up with a whiteboard or something. This would make it easier, but no such luck. So, my mean. Okay. My mean here is my X bar, which is, you need to write that, which is this 568.125. Okay. My standard deviation, so that's same thing as your standard deviation. S sub x is 109.48. Okay. My Q1 is 510. My median here, I'll scroll down to 600. Okay. My Q3, I believe is what I asked for next, is 637.5. Okay. And let's see what else we asked for. IQR and range. Okay, so my min here is 350, my max is 700, which should give me 350 for my range, right? IQR, my Q3, minus my Q1, you can use your calculator for that one, 637.5 minus 510. Get 127.5. Fair enough? Everybody okay? Easy enough to find on the calculator. Hopefully you can do that part. Okay. Now, in order to see how it kind of transforms, it says, now find new values for the data set if I were to make $100 more each weekend. So, if I start with my original data set and add 100 to each, then my new data set looks like 600, 700, 725, 700, 800, 750, 620, and 450. all I did was add 100 to each one of these values, put them in my new line to make me a new data set. Okay, I made $100 extra every weekend, so I'm just adding 100 to those. Everybody okay with that? Not rocket science. It's vegetable science. Okay, so I'm going to type my new list in. So 600, 700, 725, 700, 800, 750, 620, 450. Got my new list typed in. Okay. So what I'm going to do, I'm going to hit stat, calculate. I'm going to calculate my new statistics on my new list. Okay. So for my new list here, my new mean is going to be 668.125. My new standard deviation is going to be 109.48. My Q1 should be 610. My median, my venture to guess is 700. My Q3 should be 737.5. Okay, my IQR, my range. Okay. So my biggest value now is 800. My smallest value now is 450. 800 minus 450 still gives you 350. My IQR, looking at 737.5 minus 610, which should still give you 127.5.
I'm sorry, I got a little bit behind. Where did you get the new score? Yeah.
Yeah, those, all I did here was, it says, now find the data values for the set, or find the values for the new data set if I were to make $100 more each weekend. So I'm saying, okay, next year I'm going to make $100 more each weekend, and I want to see what that's going to give me. So all I did was add 100 to this, made my new data set, typed it in, found my new statistics. Okay. Now if we look at how everything changed, here the mean, how did the mean change? Yeah, all we did was add 100, right? Standard deviation stayed the same, didn't change, right? So didn't change, stayed the same. I'm just going to leave it alone. Okay. Q1 just added 100, right? Okay. Median just added 100. Q3 just added 100. IQR stayed the same. Range stayed the same. So if you want to put same, you can. Same, no change, whatever. What does that tell you about an addition or subtraction transformation? If you just add to your data set as a whole, so if you add a number to your entire data set, then you're going to add to your mean, your Q1, your median, and your Q3, but your standard deviation, IQR, and range stay the same. Okay. So instead of going through here and say this data set's like 40 different points and having to add 100 to 40 different points, all you have to do is add 100 to your mean, leave your standard deviation the same, add 100 to this, that stays, right? So instead of having to redo the entire data set in your calculator, what I'll do is I'll say, okay, next weekend I made $100 extra, or the next year I made $100 extra per weekend. What are my new statistics? How does it change? You'll say, okay, instead of typing in this data set of 40, or however big it is, in my calculator, all I really need to know is that I'm just going to add whatever that number is to the mean, to the Q1, to the median, to the Q3. These other stuff stay the same. Okay. Everybody okay with that? So addition and subtraction, you only have to really worry about changing 4 values. Everything else stays. Okay. The next set here says now find the following values for the new data set. Let's see, what is that? What was affected by adding $100 per weekend? Obviously that was the mean, Q1, median, and Q3. You wanted to put that in there, fill out your notes. After talking it over with a friend of mine who was an expert at advertising on Facebook, I decided to let them make me a business page and manage it. She claims that my business will expand by 25% every weekend because of the new advertising. Find the new values for this data set. Okay. So for this one, I'm going to put this new data set over here. So we're going to expand my business by 25% from the original, not from the second one here. We're going to start back at these original data values, and we're going to expand it by 25%. Okay. So I need to do 500 times 0.125, so 1.25. My new data set will look like this. My first value will be 625. My next value will be 600 times 1.25, 750. So I'm gonna do a couple of them and then walk over there, so I don't have to back and forth it so much. I already have the 600 times 1.25, but I want to keep myself straight, so I'm going to do it twice. And let's go ahead and write these up there. We've got 750, we've got 781.25, we've got 750, we've got 875. Everybody okay so far? Everybody see why I'm doing it times 1.25, not just 2.25, right? If I'm increasing my business, and I would have done 700, I'm increasing it by 25%. I just multiply it by 0.25, I can only get 175. That's obviously not an increase. You have to go back and add it to your original. The easiest way to do that is just do times 1.25. It's like an economic thing, yeah. So, let's see, still need to do 650. 650 times 1.25. Need to do a 520 times 1.25. And a 350 times 1.25. Alright, so 812.5. 650. 437.5. So our new data set looks like that. So that's what I would put right here in that 25% range area. Okay? Alright, so now that we've done all that, what we're going to do is we're going to find the new values, or find the following values for the new data set, the mean through the range. So I'm going to go back into my calculator here, stat edit, type my new list in. Okay, clear the old one out, type new one in. Looking at 625, 750, that's 781.25. Oh. 750, 825, that's 875. 875. We got 812.5. We've got 650. And we have 437.5. I think I got all those typed in correctly. Stat calculate, we'll calculate the statistics on it. And we get our new ones here. So I'm just going to assume you'll go through and see what we're doing here. Alright, so my new statistics here, we're going to look at your mean, standard deviation. My new mean is 710.156, I don't know. Not really big on rounding. 136.85. Next thing we wanted was Q1. Okay, Q1 here is 637.5. Median, 3. IQR. Range. Okay, go on top of these. So median, 750. 3, 796.875. IQR is going to be 796.875 minus 637.5. Range is going to be 875 minus 437.5. What's the IQR? It's right here. What? 159.375. What about the range?
437.5.
437.5. That's me. All right. So when we added 100 to everything in the data set, right? We had a few values that had 100 added to it. Everything else stayed the same. Here we essentially multiplied by 1.25, right? That's what we did to everything. So we multiplied by 1.25. So if we go to our original stuff, so if I look at my original value here, I take my calculator, I look at 568.125. I multiply that times 1.25, I get exactly what we got over there, right? Do the same thing for standard deviation, 109.48. Multiply that by 1.25, I get exactly what we got over there. So Q1, same thing, 510 times 1.25, and get exactly what we got over there.
Can you explain the, I'm sorry,
Yeah, you did.
the 1.25 again?
Okay, so
So every time that we're gonna do like,
like here, I wanted to increase the business sales by 25% per year, right? So if I had made $100, right, but I wanted to increase, I want to increase by 25%. If I were to just multiply 100 times 0.25 for my increase, I'll get $25, right? $25 isn't an increase from 100. What you forgot was I'm increasing by 25% from 100, so I'm increasing by $25 from 100. You kind of have to add the two. 125, right? So instead of doing two steps, if I just multiply 100 times 1, which is my original 100, and the additional 25%, that gives me the 125%. Does that make sense? Yeah. So, everybody good so far? Please do stop me if you get confused, because I'd rather you catch it now than be confused the whole rest of the time. Because I can go fast sometimes, kind of not realize it. So basically what we do here, every single one of these values, if you multiply it by 1.25 or multiply everything by, you're going to get your new value over here. So instead of having to multiply every data set point by 1.25, you can just multiply your results by 1.25. Does that make sense? So next year I want to increase it by 25%. Okay, instead of having to go back and say, okay, this data point will increase by 1.25%, calculate it. This next one, 1.25%, calculate it. Then go back through and calculate the totals on everything. Just start with the end. Say, okay, if everything's increasing by 1.25%, I I need to multiply mean by 1.25, standard deviation by 1.25, Q1, median, Q3, IQR, range, everything gets multiplied. Okay. So what it comes down to, it's kind of like a general statement of rules. Transformation. So what was affected by increasing the sales 25%? Everything was affected. All of it. Mean, standard deviation, Q1, median, Q3, IQR, range, was all affected. This general rule so for addition or subtraction, that affected what? That was your, which one's changed? Mean, median, Q1, and Q3, multiplication, or division, everything changes, right? So, you got your mean, median, Q1, Q3, IQR, range, standard deviation, I think I covered them all, didn't I? So everything changes. Everybody okay with that? Okay. The next question, it basically gives you, it says if the same number is added or subtracted to all the data items, the transformation is a shift of new data. If all the data items are multiplied or divided by the same number, the transformation is a rescale. Okay. Without creating the actual data set, find the new measures of the data set. I don't know what to do. Just follow it on board. Alright, so essentially what I really wanted to do here, I'm not sure what I'll think of here. If you wanted to take your new data set, okay, and I wanted to basically add $100 every weekend and increase it 25%. Maybe that's what I said there. I just didn't mean that. But it says, I like to fish bass tournaments on the weekend. What to do? Tournaments can have expensive entry fees ranging from $100 to $1,800 per tournament. After picking the tournaments I wanted to fish, I determined I need to do both. Increase my sales by 25% and still sell 100 more than that, so I can afford to actually fish those tournaments. So my new sales for my vegetable farm need to be 125% or 1.25 times X plus 100. So I want to make 25% more each weekend and an additional $100 on top of that. Right? Okay. So, which part's the shift, which part's the rescale, follows directly from the definition. Okay, the definition says, if the same number is added or subtracted, transformation is a shift. Okay, the addition is the shift. The multiplication is the rescale. Okay. Alright, so the bottom part says, out creating the actual data set, find the following measures for the new data. What you're supposed to do here, okay, kind of follows this formula, right? So I've got this sales formula. Sales equals 1.25x plus 100. So if I start with my original data set here, so I can't perfectly erase. What was my Q1 here? It was 510 point something, 125?
Just by 10.
510? Okay, what was standard deviation?
109.
Alright. So instead of having to transform each data point, what I can do is start here. Okay. Mean is affected by two things, right? Mean is affected by the addition and the multiplication, right? Your standard order of operations say you do which first? Multiply, right? Okay, so we're going to multiply first. So I'm going to take my mean here, 568.125. I'm going to multiply by that 1.25, and then I'm going to add 100 to it. Okay. So my new mean is 810.16 approximately. Now my standard deviation. My standard deviation is affected by what? The multiplication, is it affected by the addition? No. That means that I don't need to add 100 to it. Okay? So all I'm going to do is I'm going to take it, the standard deviation was 109.48. I'm going to multiply it by 1.25, but I'm not going to add the 100 to it because the 100 doesn't affect it. It's not affected by addition. So my new standard deviation is 136.85. Okay. Q1, median, Q3, IQR and range. Okay, my Q1 is affected by what? Addition and multiplication, right? So I got to do both. I'm going to multiply my Q1, 510, times that 1.25. I'm going to add 100 to that. So I get 737.5. Median is affected by both, so I'm going to do both. Okay. So 600 times 1.25. I'm going to add 100 to it. 850. Q3 is affected by both, so I'm going to do both to it. Q3 is 637.5. Multiply by 1.25, add 100 to it. Giving 896.875. Two more. IQR and range. Is IQR and range affected by addition or subtraction? No. But it is affected by multiplication and division. So the only thing I'm going to do both of those is multiply by 1.25. I don't have to add to it. Add to it to myself. So IQR is 127.5. Multiply that by 1.25. Range is 350. Multiply that by 1.25. So I'm not going to add that 100 to either of them because they're not affected by the addition. So 159.375 and 437.5. Okay. Sorry if that got a little confusing. Where is that? I'll fix it for next semester, but none of you will be here to see that, hopefully. Okay. The biggest thing, usually what I'll do is I'll give you the information. So I will, just like I did on the quiz, I'll give you a set of data, right? Just like you had on your little quiz right here. It'll give you the little bar or whatever, I'll have all your information. And I'll say, okay, I want to transform this, and I'll give you the equation I want to transform it by. I want to transform my sales like this. What is my new set? And I'll have like a blank table with your new set of data. You have to fill it out, okay? Where everybody messes up is they absent-mindedly just plug every single thing into this equation, okay? You don't want to do that. Some of them you do, some of them you don't. Your mean goes into the equation just fine. But when you get to your standard deviation, if you plug it in and you forget to drop off the 100, you're going to get the wrong answer. So a lot of times what happens is everybody gets the mean, median, Q1, and Q3 right, and everybody else gets the IQR, range, and standard deviation wrong because they forget that they don't need to add 100 or whatever that number is to it. Okay, so that's what you have to be careful of. Those aren't affected by addition or subtraction, So don't add or subtract to them. If you can remember that, you'll get that question right. Okay. What I have here is a graphical representation of what a transformation looks like. Okay. So pretty sure everybody is familiar with Celsius to Fahrenheit. So Celsius to Fahrenheit is just a temperature difference, right? It's a difference in how we measure temperature. What you should notice, if you transform something, it shouldn't change the shape at all. Nothing should really change. The only thing that changes is basically your numbers on your axis. Okay. Now, obviously there's a shift to the right of 32, and your scale changes by the 9/5, right? So notice the same shape is maintained. However, look at the x-axis, we notice that the scale has changed. Was the scale affected by the 9/5 or the 32? The scale was affected by the 9/5. 32 just caused a shift. Okay. The rescale is your multiplication, which is the 9/5. The shift is your addition subtraction, right? Does that make sense? But it shouldn't change the picture. I've done these before where I've made people like do like a multiple choice question and made them pick the graph and stuff like that. You'd be surprised how many people would think that this would actually change the picture. It doesn't at all. The picture stays the same. Only thing it changes is the units on the bottom. Alright. Shifting, scaling, and z-scores. Standardizing into z-scores does not change the shape of the distribution of the variable. So when we standardize into z-scores, all we're doing is basically exactly what we did here. We're just doing a shift or a rescale. It doesn't change anything, it just changes the units. It standardizes the units. Okay, standardizing the z-scores makes the center 0, makes the standard deviation 1. Okay. The reason we do that is so that we can hopefully put it into a normal model. If it follows a normal model, there's a lot of things we can do with it in order to kind of draw conclusions on it. So normal models are appropriate for distributions whose shape are unimodal and roughly symmetric. This is why they're commonly referred to as the bell-shaped curve. We write normal with your mean mu and your standard deviation sigma to represent a normal model with mean mu and standard deviation sigma. Mean, or mu and sigma, are what we call parameters of the model. They are the numbers we choose to specify the model. So this is a picture of a normal model. You got your bell-shaped curve. You got your center. You got your mu, and each one of these has a standard deviation hat. So I've got one standard deviation to the right, one standard deviation to the left. Between there is 68% of my data. You got two standard deviations to the right, two standard deviations to the left. Between those two, 95% of my data. Three standard deviations out is 99.7% of my data. Okay, so we can capture that much data by going out those many standard deviations. A normal model when your mean is 0 and your standard deviation 1 is called the standard normal model. So if I started out here, this was 0, 1, 2, 3, -1, -2, -3, that would be a standard normal. Okay. And when we transform into z-scores, that's essentially what we do. So how would the graph look for the standard normal? It would look just like that. All you'd have different would be your axis here. It would be a 0, 1, 2, 3, -1, -2, -3. Okay. Properties of normal distributions. Normal distributions have one mode. They're symmetric around the mode. The mean and the median, the normal distribution, are both equal to the mode. In other words, the mean, median, and mode are all the same. Okay. Remember, the mode is just the peak of the graph. Normal distribution follows the empirical rule, which says that 68% of the population is within one standard deviation of the mean, 95 is within 2, and 99.7% is within 3 standard deviations of the mean. That's exactly what our graph says. 68% within one standard deviation of the mean, both directions. 95% within 2 standard deviations of the mean, both directions. 99.7 within 3 standard deviations of the mean in both directions. Okay, how do we determine if a data fits a normal distribution? Okay, the first thing we'll do is we'll check the nearly normal condition. distribution is unimodal and symmetric. How do we do that? A lot of times we make a histogram. Okay, so I've got this data here. I'm not sure if I updated the graph. I didn't update the graph correctly, so we'll have to do a little bit of finagling with the graph. So let's have a look at it. Okay, so suppose the following data consists of 22 respiratory rates randomly selected from 179 adult patients who have visited a clinic on Saturday. Struck a histogram of the data. Okay. So we got all this. Okay. In order to do a histogram, what I'm going to do first is put all this data in my calculator. Okay. So I'm going to come over here, clear this out. I'm going to clear my list out. So stat edit. I'm going to go up here, hit clear, and enter, and that clears my whole list out. I'm going to type this in. Order doesn't matter. So I'm just going to go down the road. So 14, 8, 13, 16, 15, 17, 18, All right, so I've got my data points put in. Everything right. I'm gonna bring out my calculator. So I really don't want to mess this up. Mess up the whole rest of the lecture. All right, so stat calculate. I'm going to calculate my statistics on my list so I can have them. Okay. Now, if we're doing a histogram, what I need to know is I need to know my min, I need to know my max. Okay, so my min here is 8, my max is 20. Okay, that means my range is, let's see, 20 minus 8 is going to be 12. All right. Now I have to decide how many bins I want. Okay. So I'll look at it here, and I had updated this, it just didn't save because they're supposed to be, you notice your lowest data point is an 8. The graph only goes down to 10. That's an error, so I'm going to draw an extra bar on it. So let's see, that'll make it, my highest one's 20, so 1, 2, 3, 4, 5. Let's do 5 bars. Or bins, if you want to call them bins. Okay. So if I'm doing 5 bars, I'm going to divide 12 by 5. Okay. 12 divided by 5 is 2.4. Okay. I'm going to round up, right? So about 3. If I start at, and to make this work, I hate that I did it like this. To make this work on the graph, let's just change the horizontal axes. So just scratch these numbers out here and below them write the correct numbers. That's the best way to do it. Apologize that I screwed that up. Try to change my examples year to year, and sometimes I don't get everything right when I change it.
You forgive me.
Huh?
You forgive me.
Yeah, I hope so. It won't hurt my feelings if I'm not. So we'll start with 8. We'll go to 11, 14, 17, 20, 23. Okay. So if I start with 8, okay, and I go here, 8 up to 11, but it doesn't include 11. Remember, your right hand endpoint goes to the next. So 8 to 11. So I've got 1 value here, 2. Looks like I got 3. Everybody agree with 3?
Yeah.
So Okay, 11 to 14. Okay, now where'd I mess up? I wasn't supposed to include what? 11. So this is actually supposed to be
2.
all right. I gotta watch. Sometimes I do it intentional, sometimes I don't. Okay.
What was that?
So 11 to 14. Okay, we do include 11, we don't include 14. So 13 is included, so I've got 1 here, 2 here,
No.
3, and what, 4? Okay. Everybody get so far? Now 14 to 17, but I don't include 17, so I'm looking at 14, 15, and 16. So 1, 2, 3, 4, 5, 6, 7, 8. Yeah, 8.
Oh, I thought we included
9, 10. I got 10. It's hard for me to look from the side. I promise you, it's hard to look. So I got 10. Everybody agree with 10?
Yeah.
Okay. 5, 6, 7, 8, 9, 17 to 20. So I include 17, I don't include 20. We're looking at 17, 18, and 19. So 1, 2, 3, 4.
4.
Just got 4, right?
Mm-hmm.
Here. And then 20 to 23 just includes 20. Okay. So I got 1, 2. So, man, I'm glad I changed the axis on that. If you don't change the axis, just write it, doesn't look right. Okay, so nearly normal condition says it's unimodal and symmetric. Is it unimodal?
Yeah.
Yeah, it's unimodal. It's got one mode. Is it symmetric? Yeah, it's symmetric, right? So, do we think it's going to be normal? Yes, right? So it passes the nearly normal condition. So, what characteristics of the histogram that would make you believe that the normal model is appropriate in general is unimodal and symmetric? Okay. Does this histogram lead you to believe the normal model is an appropriate approximation? I would say, yes it does. Right? This one's freaking perfect. They don't always turn out being perfect. Okay. Alright. Now, let's check for normality using the empirical rule. Okay. So if you put your data in your calculator, which we already have, under L1 and calculate the mean and standard deviation rounded to the nearest hundredths place. So we've done that. Just got to scroll up here, my mean. So tenths, hundredths, so my mean is 14.73. So I'm going to go over here, 14.73. Standard deviation is 2.91. Okay. Everybody okay with those two numbers? B says construct the intervals that define the following: 1 standard deviation from the mean, 2 from the mean, and 3 from the mean. So, 1 standard deviation from the mean. We're going to look at it on both sides. So our mean here is 14.73. So I'm going to add 1 standard deviation to it, which is 2.91. And I'm also going to subtract 1 standard deviation from it. See what numbers I get. 4 on the upper side, I get 11.82 on the lower side. Okay. So that was one standard deviation. Let's look at two standard deviations. So 14.73 plus, I'm going to do 2 times 2.91. 14.73 minus 2 times 2.91. Okay? If you want to just subtract 2.91 twice, you can do that too. Do this. So, looking at 8.91 and 20.55. So, okay. The other one I have to look at is 3 standard deviations. So 14.73 plus 3 times 2.91. 14.73 minus 3 times 2.91. Looking at 6 to 23.46. 6. Everybody good here? Okay. Calculate all these. Calculate. Pretty easy to calculate. You should be able to do this. You have the mean standard deviation. You don't need to know anything else but the mean standard deviation to calculate. Now, C says give the percentage of values in each interval. First interval, second interval, third interval. I'm going to go up here to our respiratory rate. And we're going to find percents in each of those values. And I'm going to write it in per. So how many of our values are between 11.82 and 17.64? Basically, we're looking at values that are 12, 13, 14, 15, 16, and 17. Okay? So you have to help me with this, because I have a hard enough time with this kids. This one counts, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9. Does that one count? Number 10, 11, 12, 13, 14, 15, 16, 16, right? I believe it's 16. It is 16. So, in our first interval, so 16 out of 22 values, right? Okay, everybody good with that? Okay. Our second interval goes from 8.91 to 20.55. Okay, so basically from 9 all the way to 20. What's the only one that's not in 9 to 20? That 20 is less than 20.55, so it's the only one not included is 8. So it should be what, 21 values? 21 out of the 22. 6 to 23.46. That's our third boundary set, right? Our 3 standard deviation set. Everything's included in that, right? So here we have 22 out of 22 values that are included in our 3 standard deviation set. Now, what that empirical rule says is that in your first standard deviation, you're supposed to have what? 68%, right? Second standard deviation set is supposed to have 95%. Third is supposed to have 99.7%. Right? Let's look and see what 16 over 22 equals. So 16 over 22 gives me 72.7. Go ahead and do 21 over 22 as well. Save me the trip. Okay. So this is 72.7. This is 95.5. Obviously, 22 over 22 is 100%, right? Now, say I didn't have the histogram to look at, or the histogram wasn't perfect like it was. Another way I can determine whether or not it's approximately normal is look at the percents. Are they close enough? Well, this one's dang near close. That one's really, really close too, right? It's only off by 0.3%. This one, a little high, but honestly not that bad. It's off by what, like 4.7%, less than 5%? So if I was just looking at the percents here, I would say, judging by the empirical rule, it's approximately normal. It's close enough for me, right? Don't expect everything to be exactly 68. It's not going to happen in this lab. It's not going to happen in real life most of the time. Okay, so answer that. We got all these filled out. We gave the percentages. If we followed an exact normal model, what would you expect those percents to be? First one would be 68. The second one would be 95, 99.7. Do you think the percentage in part C are close enough to consider the distribution nearly normal? Yes, I do. Okay. The answer to E, I need to write it, would be yes. Close enough. All right. On to page 7. Okay. So, another way we could check, so we've got 3 ways so far, or 2 ways so far. Histogram, we can check by the percentages from the empirical rule. The other way we can check is using a normal probability plot, or sometimes it's called a normal quantile plot. So if the normal probability plot is roughly a diagonal straight line, and the distribution of the data is roughly normal. Deviations from a straight line indicate the distribution is not normal. So how do we do this? First thing, you're going to clear all your lists, but don't do that because we already have our list typed in. Okay. So enter your data into list 1. Now we're going to go to the calculator. It's going to say press second, y equals. Okay. It's going to bring you to your stat plots. Okay. So stat plots. You need to turn your first plot on. So plot 1, I'm going to press enter. That's going to take us to plot 1. We're going to turn it on. So it's blinking on 1. I'm going to hit enter on. It's going to turn it on. Okay. Next thing we're going to do, I'm going to use the arrows here, and we're going to select the normal probability plot, or the normal quantile plot, or whatever you want to call it. It's the one on the bottom right, or if you've got one that looks like mine, it's the very far one on the right. It looks like a line. Okay. So we'll go over there, and we'll hit enter on it. Okay. It should have your list 1 already selected. Don't mess with anything else. If you want to change the mark, you can. I'd suggest just leaving it alone. If you want to change the color and it be green instead of blue because you weren't a Blue Devil and you hated them in high school or something, whatever your reason is, you were the Green Hornets or something crazy, something like that, that's fine. I don't care. Change color, whatever you want to be. That's fine. Now what you're going to do after you got all that typed in, you're going to press zoom and then do zoom stat. So zoom button's right up here up top, right in the middle, zoom. We're going to scroll down, stat is number 9. Okay. Now I will tell you, if you have something in your y equals already, like a formula, go ahead and clear that out. So if you had a 3x times 2, or whatever, 3x plus 2 from Algebra 1 or whenever you took it, clear that. Zoom, you can press 9 for stat, it gives you this. Okay. Now what we're looking at here, does this look like an approximate straight line? Does to me, right? Okay, it's not going to be perfect. You've got a few that deviate a little bit, but for the most part, if I drew a line, it would be pretty dang close to most all those points. Okay? So by the normal probability plot, or the normal quantile plot, I would say this is approximately normal. Okay? That is the easiest way to do it. Okay? Don't want to draw a histogram. Don't feel like calculating percentages. Type list in your calculator. Do a normal probability plot. And see if it's an approximate straight line. Okay? Okay? The way I would write that up, okay, so we did that. Does the data look roughly normal? Why or why not? So if I did that, what I would be expecting from you, if I ask you if the data was normal, the way I would expect you to respond, because I hate it when you respond and you give me nothing, I would say, yes, it is approximately normal. The normal probability plot is an approximately straight diagonal line. You just say yes, you're gonna get half credit off. Okay, gotta give me a reason. Show what you're talking about. I know a lot of you just like to guess. Like, I don't know the answer to this. I'm this class. I'm gonna put yes. It's 50-50 chance. It's 50-50 chance you get half credit. It's better than nothing. Okay, so when we start doing bigger examples with bigger numbers, it'll look more like a line because you'll have points stacked on top of each other. So basically what this is actually done in R, not in the TI, but it looks the same. It gives you your distribution and it compares it to the normal quantile plot. They call it a normal QQ plot. It's the same thing. So here we have a symmetric distribution. It's an approximately straight diagonal line. Okay. Skewed right, or a positive skewed, it's not a straight line, it's a curve. Right? Okay. It actually kind of curves up. Sometimes you have what we call fat tails, which just means that you have more values on the end than normal. It's still an approximately straight line. So if I was given this normal quantile plot, I would say it's approximately symmetric in this class. I don't expect you to be able to call out fat tails in this class. It's not what this class is for. Okay, but I do expect you to be able to identify the skewness. Okay, and not necessarily negative or positive from the quantile plot, but just say, okay, this is not a normal probability plot. Okay, this is not a straight line. It's not approximately normal. Okay, might be skewed. Okay, if you notice the skewed left, it's curved down. If it's skewed right, it's curved up. Okay, so if I gave you a normal probability plot, you should be able to say, yes, it's normal. No, it's not. Why or why not? Yes, it's normal. It's a straight line. No, it's not normal. It's not a straight line. It's curved. Okay, that's kind of what I'd be expecting. Simple enough. All right. Told you this was gonna be a long one. Got a few more pages. We'll see if we can get through them and round it on out next class. All right. So these are pretty easy examples. To sketch a normal curve for each distribution, label the x-axis at 1, 2, and 3 standard deviations from the mean. Okay. I give you the mean is 75. The standard deviation is 8. Gives you the picture. You got your curve here. Okay. Your mean always goes in the middle. So your middle value is 75. Right? And you got 1, 2, 3. 1, 2, 3. One standard deviation to the right just means I add 3 to 75. 75 plus 3 is 78. So this one would be 81, right? This one would be 84. And I work my way to the left. This one would be, this one would be, this one would be. You're done, right? Okay. So the other thing I could ask you with a question like this: between 72 and 78, how much of my data lies between 72 and 78? 68, and 69 and 81, 95, and between 66 and 84, is at 99.7%. Okay. All right, number 2, same thing. Still have our curve. Mine isn't as good as the one on the screen, but your middle here is 98.9. To go 1 standard deviation to the right, I need to add 0.8. 98.9 plus 0.8, it's going to give you 99.7, right? Add another one,
100.5.
100.5. Add another one,
101.3.
101.3. If I go to the left side, 98.8 minus 0.8 would be 98.1, right? Next one would be,
97.3.
and the next one would be 96.5.
5.
Okay. What percent lies between 98.1 and 99.7? 68, 95, 99.7. Not rocket science. All right, number 3, they give you a graph, but it does give you the normal model. It says, given a normal model, 56, 17. Okay. So, which one's my mean, which one's my standard deviation? 56 is my mean, my standard deviation is 17. Okay? If you know that, these questions become really, really easy. In what interval do you expect to find the central 68% of values in this distribution? That's A. We're looking for 68% of our values. It needs to be in an interval. How many standard deviations do I go for 68%? 1, right? So I need to do 56 plus 17 and 56 minus 17, right? 56 plus 17 is what? 73. And 56 minus 17 is 39. Always write the lower one first. Okay. All right. Now we're looking for what? 95%. So I need to go 2 standard deviations. So it needs to be 56 plus 2 times 17. 56 minus 2 times 7. So my lower is 22. My upper is 90. Right. So 3 for 99.7, right? So 56 plus 3 times 17. 56 minus 3 17 should give you
The highest 107.
107 to what, 5? Is that right?
5.
Easy enough? All right. About what percent of the values in the distribution should lie above 107? So let's look at I'm going to kind of draw a picture real quick. Okay, so the middle of our value for this one was 56. If I go 1 standard deviation to the right, I get 73, 90, and then 105. Is that right? You sure?
73, 90, 105.
What's 90 plus 17? One of those is wrong.
107.
107. You're gonna lie to me.
I thought that's what we knew.
Yeah, that's what it was.
Yeah.
I called it initially. Okay, now we gotta go left. So we're looking at the lower side. The first one down is 39. Next one down is 22. And then 5. Right? So we've kind of, so 68% here. Between the two greens, we've got 95%. And just enough colors. Between the two browns is 99.7, right? So what we got here, it says what percent of values in this distribution should lie above 107? Okay. So between 5 and 107 is 99.7% of my values, which means I have what left? 0.3%, right? That 0.3%, so that 0.3% is split between here and here, though, right? Does that make sense? So 99.7, I'll subtract that from 100, I get 0.3%. That's split between two locations, here, here. I want to know what's greater than 107. That's only half of it, right? So I need to divide by 2. So what percent is greater than 107? 0.15%. Does that make sense? A lot of people don't like that. Okay, so it's not as bad. We're going to look at a whole bunch of different cases. So, okay. What percent of values in this distribution should lie below 39? Okay. So I'm looking at my blues here. Between 39 and 73 is